Hi, my name is Ron Dorn. I'm a physical geographer at Arizona State University, and I've partnered with Ryan Heintzman, who's a microclimatologist and physical geographer, and two Ben Coppers to produce a laboratory for a fantastic geovisualization about lightning in the San Francisco peaks. The purpose of this presentation is to provide you the essence of what this laboratory is all about. Uh, I'll need to start sharing the screen here. This is the geovisualization for the San Francisco peaks where the avatar arrives on the top of Mount Humphreys. All around you is striking lightning. So you're standing on the highest point in Arizona, which is more than 12,000 feet high. And in this case, you're looking east out to the Painted Desert with lightning strikes. The locations of the cloud to ground lightning strikes in August are shown by these little icons. And then when I switch to an air temperature view, the icons for where the lightning strikes hit change to have maximum contrast. So you're in August and you're looking at air temperatures where the Painted Desert and the low and the high desert of Arizona is quite warm in the distance, and the peaks are quite cool, except for the east-facing slopes. The air temperature data comes from Landsat Thematic Mapper, and it's acquired at 10 a.m. So the east-facing slopes warm up pretty quick by 10 a.m. There's also rainfall or isohyet data, where at the top of Mount Humphreys for the month of August, the rainfall total averages 212 millimeters. Where the avatar is, you can see the air temperature as well as the surface temperature, the latitude and longitude, the elevation, and the outer ring of the compass is where the camera faces, in this case to the southwest, and the inner ring is the direction the avatar faces, in this case to the southeast. The essence of the lab rests in having you hypothesize and understand, at least to a best guess, to a best estimate based upon learning processes, why lightning has the distribution that it does. By now, you may be wondering why the avatar at the top of Mount Humphreys doesn't have a lot of lightning strikes. So let me jump using the fast travel to a location that I know has a lot of lightning strikes. And I'm jumping to Schultz Pass, which is between Mount Eldon and the main San Francisco peaks. And all those are cloud to ground lightning strikes from an episode of a thunderstorm. There's a huge number of them striking all around the avatar. In this case, the likely mechanism of the lightning strikes is called upslope mountain winds. In the morning, incoming solar radiation strikes east and southeast facing slopes sooner and more directly than the adjacent low-lying areas. And this creates a pressure surface that draws upslope winds. So the idea is, as the inclined terrain heats up, a horizontal temperature difference develops. The temperature difference causes the pressure surfaces to dip near the mountain surface. This creates a pressure gradient and causes the cooler air to be drawn towards up the slope of the mountain. And this creates a circulation system where there are upslope winds during the afternoon. As the winds rise up in the afternoon, they'll cool, and if there's a sufficient amount of moisture in the atmosphere, you'll get thunderstorm formation. Then there's a completely different type of cluster of lightning strikes that occurs. And in this case, we're going to jump out into the middle of the flats. Let me orient you. You're in isohyets. Let's go to the Landsat layer, and you're looking at Mount Humphreys in the distance, and you're seeing a set of isolated lightning strikes all over the place. These isolated lightning strikes don't have a particular cluster, so they could be due to the thunderstorms that formed over the mountain with the upslope winds, or they could be due to an alternative mechanism, which is called surface heating. The idea here is that out in the flats, where the air temperature is quite warm and where the ground temperature is extremely warm, the air starts to heat up. And when the air heats up, you create lower pressure right at the surface. The hot air rises, cools, and then it condenses, and you get thunderstorms going. So thermals, these hot air rising, will produce sometimes thunderstorms by intense heating. And these are popping up all over the flats, and they result in lightning clusters down on the flats. So you have two basic mechanisms of thunderstorm formation in the study area of the San Francisco peaks: upslope winds and surface heating. And then you have two sort of circumstances what's happening with the steering wind of the storms. The basic configuration that you learn in the lab is that you get a high pressure to the north and east of Arizona or to the east of Arizona, and then a monsoon low with thermal heating, and this creates circulation counterclockwise in the low, clockwise around the high, and it brings the moist air northward. Where there's a strong pressure gradient between these big pressure cells, you can get a strong flow of air, and the storms will move quickly over the landscape. In other cases, the gradient between these pressure cells is much lower, and the airflow is much more sluggish. So when you get circumstances where you can get a cluster of lightning strikes on the mountain slope, the odds are is that it's upslope winds producing the thunderstorm. Where you get a lightning cluster out on the flats, the odds are is that there's thermal heating, surface convection creating the thunderstorm. But where you get scatters of lightning storms, then it's much harder to know the exact mechanism. So you can think of the process that you're going to go through in this lab as you learn about these things is that weak steering winds, you can probably know that strikes focused on the mountain slopes will be from upslope winds leading to thunderstorm formation. And when there's a weak steering flow, where the thunderstorm is basically going to build where it forms, strikes focused near the location of storm formation could be anywhere out on the flats due to surface convection. But when there's strong steering flow and the thunderstorm moves over the landscape and you get more scattered distribution of lightning, it could be from either process. So you learn about all this in the laboratory. I hope you have an engaging, fun time, because certainly there's no other way for you to analyze and figure out what's happening with lightning other than through a geovisualization process. Enjoy the lab and don't hesitate to please ask questions.